Okay, let's get started. So we're going to be talking about various kinds of tests we can perform to determine whether or not something converges, a series converges or doesn't converge. And before we do that, we need to establish some new notions of convergence. So first definition. We say a series converges absolutely if and only if the sum k equals 1 to infinity, the absolute value of ak converges. Okay, so let's think about this. Example. If we consider this series, does this series converge absolutely? Does it converge absolutely? Give me a thumbs up if you think yes, and a thumbs down if you think no. Most people give me a thumbs down. Okay, someone who gives me a thumbs down, give me a reason why. Right, which is this harmonic series, which we've learned doesn't converge by the integral test. Yeah? So this thing definitely doesn't converge absolutely, but does it converge at all? Does it converge by itself? Some people say no. Okay, give me a thumbs up if you think it does converge, thumbs down if you think it doesn't. Yeah, it's decreasing, and therefore it's you're almost there. Therefore it is a alternating series, right? The series is just going, in this case, it starts going backwards, then forwards, then backwards, forwards, like this, converging ultimately. Yes, this is an alternating series. So this converges, but does not converge absolutely. So I'm going to abbreviate absolutely to ABS from this point. Another example, what about this? Does this thing converge absolutely? Give me a thumbs up if yes and thumbs down if no. Perfect, yep. So the absolute value of this is just 1 over k squared. K2 is bigger than 1. It's just a p series, and therefore we know it converges. So this thing converges absolutely. And does it converge in the ordinary sense? So if we just look at this series by itself, does it converge? Right. It's just an alternating. Perfect. It is another alternating series. So yes, for sure it converges. So this thing both converges absolutely and converges. Huh? Okay, so these notions are definitely different. These are definitely different notions of convergence. And in fact, converging absolutely is the stronger notion. It's a stronger notion. If something converges absolutely, it converges. Okay, and let's just state that as a theorem. If a series converges absolutely, then it converges. And this, I want to show you why, because it's very quick and easy to see why. All we do is look at the following inequality. We know for sure that if we take the terms of the series and then we add the absolute value like this, then it's got to be bigger than or equal to 0. Yeah? If ak is positive, then for sure that's true. And if ak is negative, then it's still true, because then that's obviously true. And it's also obviously true that this thing is less than twice the absolute value of ak. Yeah? So, since we're assuming that a series converges absolutely, this thing, the sum of the absolute value of ak, converges. Yeah? So therefore, twice the sum of this thing converges. So sum k equals 1 to infinity, 2, absolute value of ak converges. Yeah? Which means that this thing here, this series from 1 to infinity, ak plus absolute value of ak, this is a series of positive terms by this inequality, which is bounded above by a series that converges. Yeah? So by the comparison test, this thing also converges. Yeah? Yeah? So we have this series that converges. Yeah? And we also know that this series, once again, converges because that's what we're given, that the series converges absolutely. So the actual series we're interested in, which is the sum from k equals 1 to infinity ak, is just the difference between these two guys. The sum k equals 1 to infinity ak is just the sum from k equals 1 to infinity ak plus absolute value of ak minus the sum from k equals 1 to infinity absolute value of ak. This converges and this converges, so when we have convergent series, we can treat them just like finite sums. Everything that's true for finite sums is true for convergent series. Particularly, we can subtract them. Yeah? So if we take this thing and subtract this thing, we just end up with this thing, and therefore this thing converges too. And that's it. So it's just one line, or maybe two lines, to see why this is true. And this is all pictures, but because I have a lot to cover, I'm not going to draw what this says. So I'm using the language now, and I'm not going to explicitly turn it into pictures. In terms of the language, this is rather quick. This is rather easy to see. Yeah? So, what does that mean? That means that converging absolutely is a more special property than converging. If we do this big blob here, this big blob represents all the series that converge. Yeah? So then the way to visualize this theorem is that the set of all the series that converge contain a proper subset, a subset that is strictly smaller, which is the series that actually converge absolutely. Because we've seen that there exist examples of series that converge, but do not converge absolutely. So this guy right here converges, but doesn't converge absolutely. Yeah? So in this picture, this guy lives, say, here. Yeah? It converges, but it's not inside this smaller subset which converge absolutely. Yeah? Whereas our friend here, this guy, both converges and converges absolutely, so it lives inside this subset. It's one of the more special ones that converge absolutely. Yeah? So converging absolutely is a more special property. Is everybody with me? Okay, so, cool. So we have these different notions of convergence, and the main takeaway you've got to have is this picture. Converging absolutely is a stronger property than just converging, and solidify these things with these examples. That this guy definitely converges, but doesn't converge absolutely, whereas this guy converges absolutely. Yeah? And also converges. Yeah? And whenever something converges absolutely, it definitely converges. Yeah? It's a subset of the set of series that converge. Cool. All right. So these are new notions of convergence. And now we're going to learn a test that tells us when something converges or not. And this is called the ratio test. So what the ratio, let me say in words what it says, and then I'll write it in language of maths, and then I'll explain it. So what the ratio test says is that if we look at the ratio of the absolute value of ak plus 1 over ak, and we take the limit of that thing, if that limit is less than 1, then the series converges absolutely. If that limit is bigger than 1, then the series diverges. And if the limit is equal to 1, then we don't know anything. Okay, think about what it means to have the limit of ak plus 1 over ak has a limit less than 1. Give yourself a number less than 1, say the number a half. What would it mean to have that the limit of ak plus 1 over ak is a half? Think about what that means. Ultimately, it means as we take k bigger and bigger and bigger, the absolute value of ak plus 1 is more and more like half of the guy before, right? It's maybe not quite half, but it's very close to half, and it's as close to half as you like. So what kind of a series is like that? What kind of a series do we have, do we discuss, have we learned about, where each term is more or less very close to being half of the term before? Think of a series that is like that. Give me an example of a series that is like that. Indeed, it's a geometric series, right? If we take the series just given by a half to the power k, yeah, then each term in the series is half of the guy before, right? We have encountered series that behave like this, yeah? What about if the limit of ak plus 1 over ak was not, let's think about the series given by ak is 1 over 2 to the power k, yeah? Then ak plus 1 is 1 over 2 to the k plus 1, which is 1 over 2 times 1 over 2 to the k. So each term is half of the term before. Yeah? You see what I mean? Give me thumbs up or thumbs down. Yeah? So this geometric series is a series that has this property. And what the ratio test is actually doing is it's trying to detect if underneath everything else, the actual structure of the series is the structure of a geometric series, the ratio test. Suppose we have series where the following possibilities occur. First possibility, the limit as k tends to infinity of absolute value of ak plus 1 over ak is equal to L, which is less than 1. Then the series converges absolutely. Second possibility, the limit as k goes to infinity of absolute value of ak plus 1 over ak is equal to L, which is bigger than 1. Then series diverges. And third possibility is that either the limit doesn't exist or the limit might be equal to 1. If the limit's equal to 1, then we know nothing. Okay. What is this about? So, imagine if we had that absolute value of ak plus 1 over ak was actually equal to L for all k bigger than some particular number. Suppose we had that, which is stronger than this, of course, but let's imagine and let's just see what happens as a consequence of that. Yeah? Then what would we have? Then we'd have that ak plus 1, or let me start with capital N, an plus 1 is less than, well, in this case, equal to L times an. Yeah? And an plus 2 is equal to L times an plus 1, which is therefore equal to L squared times an. Yeah? And a capital N plus 3, same reasoning, would therefore be L to the 3 times AN. Yeah? And so on. A N plus K would therefore be equal to L to the K times AN. And therefore, if we just summed from K equals capital N to infinity of the absolute value of these terms, this would just be equal to AN, the sum from K equals N to infinity of L to the K. And if L is some number less than 1, it's a geometric series that converges. Yeah? So if we had this, then it's definitely true that L being less than 1 implies it converges. Yeah? But we don't have this. We have something a little bit weaker, right? We have that the limit of this thing is equal to L. So suppose we represent that with a picture. So here is 1 itself. Here is L, it's somewhere underneath. Yeah? And if we look at these terms, the absolute value of AK plus 1 over AK, it's a sequence that converges to this number L. And that means that if we take, I'll make this smaller, if we take any little strip around L, let's make a strip like this, then ultimately all the terms of the series, absolute value of AK plus 1 over AK, are inside this strip. Yeah? Which means that all the terms of the series will ultimately be less than some number which is less than 1 itself. Because we can make this strip so small that the entire strip is less than the number 1. Do you see what I mean? Cool. All right, so let's see what happens if we don't have equality now, we have an inequality. So we can no longer guarantee that this thing is equal to L, but we know it's less than some number which is a little bit less than 1. So let's make the number, call it W. So let's make this upper side of the strip be at W here, where W is less than 1. So let's see what happens to what we just did. So we don't have this anymore. We have less than or equal to W for all K bigger than N. That's exactly what we have. That's what we see from the picture. So from this point onwards, N, this ratio is always inside this strip, and therefore we have this. That is just, in the language of maths, this picture. Huh? So it's less than or equal to W for all K less than or equal to N. So now we have inequalities instead of equalities. So now we have less than W, which is less than W squared, which is less than W to the power 3. We're doing exactly the same argument, but now equalities get replaced by inequalities and L gets replaced by W. We are still really happy now because what we've just written down is the fact that this series is bounded by a geometric series that converges because W is less than 1. Yeah? Cool. So it's easily the case that if we have this hypothesis, this information given to us, then we know that all these terms, AN over AN plus 1, are trapped within some thin strip, which is strictly below 1. Therefore, this chain of inequality is true, and therefore we see that our series is bounded by a geometric series, therefore it converges by comparison test. Yep. So the sum from K equals N to infinity, AK converges. And since the first n terms, or n minus 1 terms, does nothing to change its convergence, so the entire series converges. K equals 1 to infinity, AK absolute value converges, therefore converges absolutely. So sum AK converges absolutely. Okay. So that is why that's true. And it's rather easy. And all you have to think about is that what series are like this? Well, series that are like this are geometric series. And all this argument is saying is that this thing is so much like a geometric series, it's actually bounded above by a geometric series. Yeah, which is true. Any geometric series is bounded above by a geometric series. And if it's bounded above by a geometric series, then it has to converge. Yeah, that's all that this thing says. Cool. All right. Look at the second thing that we claim. If the limit L is bigger than 1, then we say it diverges. We claim it diverges. Tell me why you believe that. Think about a sequence of AK where this is true. Visualize in your mind what the sequence would look like. Suppose we put the sequence on this graph here, or on this picture here. So we put absolute value of A1, then A2, then A3. What is it going to look like? If I was going to keep plotting the points, what would they look like? Can anybody help? Yeah, they are, right? They are, because each term will be some bigger fraction of the last term. So if L, for example, was 2, then ultimately each one of these guys is almost twice the guy before, which means it's at least 3/2 the guy before. Yeah? Let me choose more convenient numbers. Suppose L was 3. That would mean that ultimately each guy is 3 times the guy before, yeah? Which means that after a while it is at least twice the guy before, which means each term doubles, yeah? Which is indeed getting very big, very fast. It's actually exponential growth, right? Yeah? So if we have this thing, it is wildly going to fail to converge because we need the terms to go to 0 when we sum a collection of positive terms. We also need them to go to 0 reasonably fast. Yeah? Because we're talking about absolute convergence, where we take the absolute value signs, where it's just a sequence of positive terms. So this condition absolutely kills any hope of convergence. Yeah? This can't possibly converge because the terms themselves are blowing up to infinity very, very fast if we have this condition. So this thing formally in the language of math looks rather similar to this thing, but they mean completely different things. When we have this thing, the series will converge absolutely because actually these terms are going to 0 very, very fast. This thing, it actually will not converge because the terms are actually blowing up very, very fast. And there's not the slightest hope it will converge. Yeah? Not the slightest hope. Yeah? Cool. So if we have this thing, then exactly the same reasoning. We think about the sequence of terms AK plus 1 over AK, and we can put them in some strip which is strictly bigger than 1. Right? And therefore, ultimately, each term will be somewhat bigger than the term before. And it might be just a little bit bigger. It might be each term is 1.01 times the term before. But still, if we keep multiplying 1.01 by itself over and over again, it blows up. It's exponential growth. It's just a function 1.01 to the power x. Yeah? Cool. So we believe this thing means the series diverges. It is indeed going to diverge spectacularly. It fails to converge in a spectacular way. And when we have this, which is right on the edge of these two conditions, we actually don't know anything. And I'm going to explain to you why, but I want you to think about why as I clear up the board. So think about what I just said. So what we are doing is ultimately comparing this series to a geometric series. A geometric series either where we have the sum of r to the k where r is less than 1, or r to the k where r is bigger than 1. Yeah? And when we have this, then we're not going to be able to make this comparison. So think about series you know that you don't have a hope to compare to a geometric series, and then think what the limit of the absolute value of ak plus 1 over ak would be in those cases. Okay, so let's think of a series where it's definitely not a geometric series, and let's think about what this limit of absolute value of ak plus 1 over ak would be. What series do we know that whose convergence we know that are nothing like a geometric series? Come on, we haven't just been discussing geometric series, huh? What else do we know? We do, yeah. What others? That's a good example. Can we do any others? Let's do something simpler. harmonic series. Okay, what about that? So if we have a k is 1 over k, let's look at the limit. The limit as k goes to infinity of ak plus 1, these things are positive, so I don't need to take absolute value. Then this is just going to be the limit as k goes to infinity of k over k plus 1. Yeah? Which is just 1, as you know. Yeah? So we can try and apply this to harmonic series, but we get the answer is 1. That's not telling us anything. Because, or maybe not, suppose, let's consider if we have, let's take something a little bit different, which is just this guy, right? This thing does converge, as you know. And if we look at this limit, then the limit as k goes to infinity of ak plus 1 over ak is going to be k squared, the limit of k squared over k plus 1 squared. Ouch. And again, as you know, we factor out the k's from the bottom, and then this will just be limit equal to 1. Are you all happy that the limit of this is to 1, or should I expand on it? Give me a thumbs up if you're happy the limit's 1. So k squared plus 2k plus 1, and then we factor out k squared from the top and bottom. And then the limit as k goes to infinity of the bottom for sure is 1, therefore this thing is 1. Yeah? Cool. All right, so this guy converges. So we definitely do indeed know nothing, right? We definitely do know nothing, because this guy here, the harmonic series, we calculated the limit was 1 and it diverges. This guy here, 1 over k squared, this thing converges, but limit's still 1. Yeah? So there's absolutely nothing you can conclude if the limit's 1. Sometimes it converges, sometimes it diverges. Yeah? So in this realm of more subtle behavior, this test doesn't do anything. So this test is actually, it looks stronger than it is, because it seems so kind of conclusive that we check if the limit is bigger than 1 or less than 1, and you think, okay, most of the time it's going to be one of those things, so I can just rule out a bunch of series from converging or show that they converge. But actually it's weaker than that, because what it's doing, it's detecting if a series in its bones is a geometric series. So there might be other things in the series that make it look like it's not a geometric series, but what this test detects is that if you ignore the irrelevant things going on in the terms in the series, if in its bones the essence of the series is a geometric series, that is what the ratio test will pick up. Yeah? But there are plenty of series that are nothing like a geometric series, which either do or don't converge for other reasons, and that test won't tell you anything. Yeah? It won't tell you anything. It's like some kind of an X-ray machine. You have a series, you can't really tell what's going on, it's very complicated. You take an X-ray with this ratio test, and the X-ray will tell you this deeper structure, the bones of the series. It's either geometric or not geometric. But that tells you stuff about the bones, but there's much else going on, right? If you go to the doctor and he takes an X-ray, it'll tell you whether or not you have broken bones, but you might have completely different things going on in you that have nothing to do with your bones, that still very much can affect your whether you live or die, right? So this thing isn't this kind of solve all tool that we can apply all the time, but in many situations where you see a series and you think, okay, it looks a little bit to me like a geometric series, then you can pull out this test and take your X-ray with this test, and you'll quickly find out if it is basically like a geometric series, and therefore what it will do. And if you try it and you get the limit 1, then actually you're wrong. It might have looked like a geometric series, but it isn't. It's not. And this test tells you nothing. Now we're going to use this thing. So let's do this with some examples. Let's look at this example here. Example 4. The sum n equals 1 to infinity of minus 1 to the n squared over n to the power 3. Okay, so somewhat complicated looking series here, right? It's changing sign. We have an n squared. We have a 3 to the n on the bottom. Yeah. But what I'm hoping is that you people will look at this and go, okay, on the bottom it's 3 to the n, which is blowing up very fast, and on the top it's n squared. Yeah, and 3 to the n is actually exponential growth, right? If we create a function that recovers the 3 to the n, the function that does it is f equals 3 to the x. Yeah, that's the function that does it. And that's the exponential function, right? So if we have 1, then we have 3, we have 2, we have 3 squared. So this function recovers the 3 to the n. So f of n equals 3 to the n. That's blowing up very fast. Yeah? Whereas on the bottom, the function that recovers the n squared is the function g, just equal to x squared, right? Because g of n is therefore equal to n squared. And this thing is a completely different story. This guy is indeed increasing, but it is absolutely being slaughtered by the exponential function. The exponential function blows up so much faster than the quadratic. It's a total massacre, right? So even though the thing on the top is increasing, what you should know based on your knowledge of these elementary functions at this point is that these terms are still going to 0, and you should have the intuition that they're going to 0 very fast. Basically, this thing, which is slowing down how fast 1 over 3 to the n is going to 0, is not going to have much of an effect on it. That's what I'm hoping your intuition will say to you at this point. Yeah? And with this intuition, you think, okay, well, if it's not having much of an effect, then this thing should be somewhat like a geometric series. I have a tool, the ratio test, that will tell me how much that's true. Yeah? So you apply the ratio test. So solution. Let's do this slowly so that we check we're doing everything right. So we write out our terms an like this. And then we just take this limit as n goes to infinity of the absolute value of an plus 1 over an. The minuses now vanish. We don't care at all about it. And then we're going to have n plus 1 squared over 3 to the n plus 1, and then we're going to have 3 to the n over n like this. Yeah? Let's clean that up, and that's equal to the limit as n goes to the infinity. And let's put this term here as n plus 1 over n squared, and then you're just going to have this cancellation of 3, so we have 1 over 3 here. We can pull out the 1 over 3, and therefore this is the limit as n goes to infinity of n plus 1 over n, and we've squared, and this thing we know already just tends to 1. Drop the squared from here. Yep. So this is just equal to 1 over 3. Yep. So sure enough, converges by ratio test. And by the reasoning that we had before, the reasoning I gave you before was that when we have this limit of 1 over 3, then this means that basically this guy is like the geometric series 1 over 3 to the n. Yeah? Yeah? Which is in line with what I said up here, that this guy looks like it's going down to 0 at the rate of 1 over 3 to the n, but it's being interfered with a little bit by this guy, which is slowing it down, but it's not slowing it down probably that much because exponential functions kill any polynomial, certainly a quadratic or any power. Yeah? Yeah. So the ratio test confirms that basically in its bones, this thing is like a geometric series. What this is going to is you're going to have a whole bunch of series. You have to determine whether they converge or diverge, and we're not going to tell you what tool to use. So I'm trying to teach you what tool to pick out. And this tool you should pick out when you think it's basically like a geometric series. Yeah? Or the absolute value of the terms is like a geometric series. Yeah? So if we take the absolute value of this, just forget about the -1, just make things simpler. Then this thing, I'm hoping you're going to start to see is like a geometric series, and therefore this is the right tool to use. Yeah? Basically, when you have something which has got something forcing it to go to 0 with at some geometric or exponential rate, and then something else is messing around with it. The thing which is messing around with it isn't gonna stop it. It's like an unstoppable freight train going down to 0, and putting some other stuff there to slow it down isn't going to have any effect. That's what you should detect when you see things like this. Let's do another example. Okay, this will be a somewhat different example, but let's see if you can use this stuff we've learned. What about this thing? Does this can converge? What do you think? Cool. That's good reasoning. Can you imagine you're in court and you make this argument and the defense lawyer objects to it and you have to nail this down more completely? What else could you add to that explanation, to that reasoning? It's not exactly alternating because we don't know for sure it's going plus, minus, plus, minus, plus, minus, right? Because cosine has this period of pi where it changes sign, right? Yeah, this is what cosine is like. Yeah. So if we have some integer here and the next integer is here, then it's not going to change sign from one to the next. But it's definitely changing sign, which is making it harder to figure out. Yeah? So we can't apply the alternating series test because it's not going up, down, up, down, up, down. Yeah? Yeah? But you are right, it is looking a lot like a p-series with p equals 2. So what have we learned that's going to help us? How could we make this simpler? What notions have we learned here today? We've learned conditional convergence. Oh, I didn't say that. We've learned conditional convergence and we've learned absolute convergence. Yeah? Does this thing converge absolutely? So consider the series n equals 1, absolute value cosine of n over n squared. Is this thing simpler? Is this thing simpler? Perfect. So since absolute value of cosine of n over n squared converges, so by the comparison test, since 1 over n squared converges, by comparison test, absolute value of cosine of n squared converges exactly as you say, because these terms are bounded. These terms are bounded above by these terms, and these terms converge. Yeah? So this is a convergence series. Now back to the original question. Does this guy converge? Does this guy converge? Because, perfect. So converges absolutely. And therefore, thus converges. So sometimes to prove something converges, it's actually easier to prove the stronger thing that it converges absolutely. Because taking the absolute value signs just makes it amenable to the other things that we know, like the comparison test or some other tool. And this is actually a kind of classic example of that. If you don't do this, then it's very hard to actually evaluate whether or not this thing converges because we don't have any other tools. The only tools we have when something changes sign is the alternating series test. And this is not alternating because it's just not going plus, minus, plus, minus, plus, minus. So this is another thing we can use to spread convergence. All right, so I want to do another example of figuring out something converges or not using something we've learned today. And then I'm going to do another test, state another test called the root test, and then we'll be done. Now the definition. We say something, we say a series converges conditionally if it converges, but it doesn't converge absolutely. So in the picture that I drew, where we have this blob represents all the series that converge, and this inner blob represents those that converge absolutely. So absolute convergence here. There are examples of guys that converge but do not converge absolutely. Right? And an example that we saw was this series here. So we take the sum from k equals 1 to infinity minus 1 to the k over k, definitely converges, yeah? But it doesn't converge absolutely, as we've learned, yeah? So, maybe a lot of definitions today, but keeping this picture in mind, I'm hoping that there's not too many. So this stuff, which is inside the set of things that converge, but outside the set of things that converge absolutely, are things that converge conditionally. So okay, now let's do another example. Consider this. Suppose we have the sum from k equals 1 to infinity minus 1 to the 3k plus 4 of 7k plus 9 to the 3 over let's do it like this, 7k, that's to the 3 times k to the 9. No, let's not make it too hard. Let's do k to the power 3, like this. All right, look at this. Tell me if you think this thing converges or not. Thumbs up if you think it converges, thumbs down if you think it doesn't. Tell me reasons why. Perfect, the limit's not 0. Okay, good. Let's change things around a little bit. What about this? 5 to the k over 6 to the k. Thumbs up if you think this converges. Right. So what you're saying is that because you're noticing the most important terms are the exponential terms, that you say, this thing, despite its other complexity, other things you're seeing around, this thing at its bones looks like it's basically a geometric series. Yeah? Yeah? And if we take the absolute value, it's going to be a geometric series basically 5 over 6 to the k. Yeah? Therefore, geometric series that converges. And that's true. That's what's going on here. And it's rather easy to detect because we're just trying to extract the stuff that is most significantly be growing or decaying, right? Which basically means detecting the stuff that is exponential. Yeah? Yeah. So this is the important term, this is the important term, and these other polynomial things are not important. So this looks like a good candidate for the ratio test. Let's try its solution. We're going to let AK be these terms. We're going to minus 1 to the 3k plus 4, 7k plus 9 to the 3, 5 to the k, 6 to the k. Take the absolute value of the limit. Okay, and then what happens? Well, these minus signs just vanish. We don't care about them. We're going to have 7 to the k plus 1 plus 9 over 7k plus 9. And we are going to have, 5 over 6 to the k plus 1 over 5 over 6 to the k, which will just give us 5 over 6, like this, right? I need to put the limit signs in. And then, as you see, this is just 5 over 6. So therefore, this thing is less than 1, converges by the ratio test. And indeed, our intuition that this is basically the absolute value of these terms basically gives us the series 5 over 6 to the k is true, so converges. So once you get used to doing this, and it isn't particularly hard, of identifying the structure that shows that despite any other stuff going on, it's actually something like a geometric series in its bones. This is rather fast, rather easy. Okay, final thing. This is a more obscure test. It's called the root test, but it's sometimes more useful, and it has a very similar structure, and it does a very similar job. It's trying to detect if in its bones, a series is a geometric series. And it goes like this. So if we have that, firstly, the limit as k goes to infinity, and now we're going to take the following thing. We're going to take the kth root of the absolute value of ak. If this thing is less than 1, then converges absolutely. If the limit as k goes to infinity of the kth root of ak is bigger than 1, diverges. And finally, if the limit as k goes to infinity of the kth root of k is equal to 1, then nothing. We don't know anything. Now this thing is an awful lot like the previous test in that, for very similar reasons to the ones I gave before, that would mean that this guy, ak, would be less than some number less than 1 to the power k. It's a nice little exercise for you to do the same kind of reasoning. So draw what it means for the limit of this thing to be less than 1. That means that ultimately all the terms are less than some number less than 1. And therefore, if you unwrap what this inequality says, it means that the absolute value of ak are being dominated by something which is a geometric series and therefore converges. So it's a very, very similar thing going on here. But sometimes this guy is more convenient. So, and this is far less often useful to use. More or less the only times it's useful to use this guy is when you see something where if you take the kth root, it simplifies. And here is an example. And this will be the last thing we do. Look at this. This is example 6. Suppose we have this thing, the sum n equals 1 to infinity of 2n plus 3 over 3n plus 2 to the power n. Okay? Okay, so, solution. What you should be thinking is that, okay, as n gets very, very big, then the stuff inside the bracket is an awful lot like just 3 over 2 to the n, which is like a geometric series. Again, in its bone, this thing looks like a geometric series. And the fact we have a power n of everything means that if we take the nth root, this thing really simplifies. If we take the nth root of this thing, then obviously these powers and roots cancel, and we just have this thing. And this thing is just going to tend to 2 over 3, so converges. Absolutely. So, whenever you see something where you have some complicated expression in brackets to the power n, it's almost a dead giveaway that the root test is the thing to try. And if you take the root test, this thing will dramatically simplify when you take the limit, and you'll be able to identify. And it's the same strategy. It's just another version of the X-ray machine to detect if in its bones the series is geometric series, which you should be able to identify just from looking at this and thinking about it just a little bit. Cool. All right. Sorry I overran. A lot of things to cover today. This is our test, however. These are our tests, and they're quick, they're easy. You practice them, you get good at them. This should be a straightforward topic. All right, people, stick around for the office hour. Otherwise, I will see you all on Friday. Have a great day.